Hello, all. Welcome to this online boot camp of IEEE Open Silicon Initiative under FOSSEE. So many of you have been part through our various programs of eSIM FOSSEE. And some of you were participants in the marathon. Some of you were fellowships, participated in our fellowships and internships. So we thought to invite you for this opportunity. So yeah, so this boot camp will be carried out by one of our experienced winners in the EC marathon. He was in the outstanding category, Mr. Vipul Kumar Sharma. So to give a quick introduction, Vipul has worked has an experience of 21 plus years in the semiconductor industry, and he has worked 19 years in the semiconductor labs, Mohali, and which is the oldest fab in India. And he has worked with various IITs for device fabrication. Then he has run various tape out programs, and he has also been in training education. He has trained around 1,000 plus engineering students and scientists from ISRO and various programs. So yeah, so he also leads outreach, and recently his tape out for the IHP PDK, IHP 130 nanometer by CMOS PDK was also accepted for fabrication. It was a outcome of our marathon, and he posted a nice LinkedIn post, so one can visit and check it out. So yeah, welcome Vipul. Over to you.
Thanks for the nice introduction. And just to give my background, I have been in my whole my career in analog and RFIC design. So this is my basic background. And what lacuna I find in industry and also very much in academia is like kind of analog design is bit neglected. There is a feeling among like students also and maybe institutes also like it is bit difficult. It's not as seamless or easy as the resources are available in digital design. So pretty much everything is automated there. So there is a tendency among students also and maybe colleges also to promote VLSI design basically as digital design. But I can vouch from my experience in the industry, the long experience, that analog design is also very much demanding. Maybe I think everybody knows that the although everything inside your digital devices works in digital domain, but all the interfaces which are required with physical world, it's everything analog. So you need an amplifiers, data converters, filters, what all things are not needed. So I suggest like people should also put some effort and also give some time of theirs to understand about analog design, and that's what my motivation is. Since I came in contact with Sumanto and the kind of good work which FOSSEE is doing in promoting open source basically, and that is one of my passions also, because this is another issue. Like generally, semiconductor design or VLSI design is kind of thought as like it's a very high barrier to entry. You need lot of infrastructure first in order to start with. Like you need all the EDA tools, the costliest one from proprietary EDA vendors, Cadence, Synopsys, everything. Then you need kind of very high end hardware also, yeah, because you cannot run these tools easily on proprietary tools on normal Windows laptop. So you need workstations and data centers to manage them. So all those are some of the barriers which has kind of made a image for VLSI design or something. Like it is a tough field. But I've been okay, I understand like it was there like maybe 10-15 years back it was there, but since uh, uh, like augmentation of open source, especially 5-6 years back, since Skywater and Google took that initiative, I think a lot of things have changed. So I strongly advise at least whoever I come in contact with, like you should definitely explore this field. At least for academia, I think it is must. There is no excuse for you to think like if you do not have tools and resources, you cannot enter VLSI design. Even though government is putting lot of initiative, they are giving subsidized tools through DLI, C2S, what all not. But still, there are some limitations because I have heard practical feedback from some of the users, like they struggle to get the licenses as and when they require, and they have to depend on their college and institute labs also whenever they want to access. It's not like everything 24/7 is available to them. So all those barriers can be easily contained with open source. So yeah, in series to that, I have been like interacting with other organizations throughout the world which are basically leading these source efforts. So I came into contact with IEEE. So this is their Open Silicon initiative. Okay, let me start sharing my slides and then we can talk. So, as I was telling, this initiative basically comes from the background of IEEE Open Silicon. So, this is one of their programs, uh, which is being led by different societies of IEEE. And their motivation is basically they want to give exposure to the students and also researchers, basically whoever is interested in VLSI design or semiconductor design. So it's one thing to just design a circuit, but I think the real basically kick comes or real experience comes when you get an opportunity to design and fabricate and then test your design. I think that kind of resources are still missing throughout the world. Although there are a lot of efforts put, especially by the Indian government and MIT, like they have opened SCL to a lot of academia, but still those are limited, and there are a lot of hiccups in order to access that using the commercial ecosystem, commercial EDA and PDK ecosystem. So here comes the IEEE. They have given this offer, like they have asked the people who are basically working in open source domain if they can organize the boot camps and they can basically give trainings to whoever people are interested in learning these tools and how the practical chips can be designed using open source tools and Skywater 130 nanometer PDK. And then there is an opportunity to actually get your designs fabricated. I think that's a big part of this deal, because it's not every day like you get your designs to be fabricated. That's also free of cost. Like IEEE is sponsoring this initiative. And the good thing is, like it's not like you will only get chips at end of your fabrication. You will get complete test board, because getting chip is one thing, but how to test your chips? You need a test board, PCB. You need to build everything periphery around your chip in order to get it tested, and it's another challenge for a lot of people, like at least for academia I know about, because they do not have so many resources to do all those things. So here the good part is you will get your designs in fabricated inside a chip mounted on a package PCB, and you will directly be able to test your circuit and compare it with whatever simulation results are you. So basically, if you are able to complete this process, you will be able to claim like I have a silicon proven design or IP which I have built. So I think that's a very good initiative. And since I have been associated with this initiative, I thought maybe I will talk to FOSSEE and Sumanto, and I'm glad like they have provided me their platform of FOSSEE to build this initiative. Okay, so let us, before we start actually learning about designing chips, let us first understand like what exactly is the motivation to do this basically. So like okay, so everybody understand about mobiles, I think. No, I think everybody know like what kind of revolution they have built, and this is one device I think nobody can live without. But this picture, one picture shows you maybe last 30 to 3 decades of journey of mobile phone, how it has evolved. On the left side you can see pretty much the first model of mobile phone which existed in somewhere around maybe late 70s or 80s. I think it was built by Motorola. It was a bulky handset device, and the only purpose of this was to transfer your calls, audio calls, nothing else. It was a big deal at that time. But you can see how much it has evolved, and today in our pockets everybody carries these mobile phones, and what all it cannot do, everything, pretty much everything. Not only voice, I think that's the secondary feature now, but you use it for every other requirements which were for which we needed different devices earlier. Like you can take a picture, record video, shoot anything, high definition videos, and basically browse the whole internet in your palms. So that kind of evolution has taken place. This is one example of mobiles, because this is one thing which I think everybody can correlate to. But I think pretty much in every domain of human life, electronics and basically the technology behind it, driven by semiconductors, had played a big role. Okay, so what lies inside a mobile phone? I think not everybody is aware of. I believe you all are from technical engineering background and maybe electronics, most of you. So you understand like what exactly lies inside it. It's not only one thing. There are a lot of different technological domains which lies inside a mobile phone. You have different kind of like sensors, optical sensor, cameras, audio sensors, microphone, speaker, everything, MEM sensors. But the primary thing I think which has driven towards this miniaturization is the ICs, the chips, which we basically understand them as in layman term. We call them as chips, but technical term is integrated circuits. And this is one technology without which, if those integrated circuits would not have been possible, I think we could not have seen the kind of revolution which we are living in today's world. So if I talk specifically about a mobile phone, so you have a mobile processor. Leading one is like Snapdragon from Qualcomm. And what lies inside this chip? This is like a high-end chip I'm talking about. I think pretty much every these concepts apply to every chip, like what kind of revolution or benefit they have provided. But this is a typical case of a mobile phone. There is a mobile processor. It is maybe built by Qualcomm or Apple or Broadcom, whoever. But if I talk about a leading edge mobile processor, let's talk about Apple's M1 processor. This was built in 5 nanometer process, although it is also now like a 3 or 4 years old process, because world is now moving towards 2 nanometer and lower processes, and it consists of 16 billion transistors. Okay, so I think everybody talks about there are so many millions and billions of transistors on a chip, but in order to make out a real sense of like what exactly the scales which we are talking about, I think this next example will help you understand that. So let us say this is like a human being. He's lying on a bed, and he's captured in a scale of around 1 meter. If we take a picture of him from the top, and now if we try to picture this same human being from, let us say, 1 kilometer above, like the order of three, if we take it, then this is the kind of picture we will see. Let us not talk about taking it from, let us say, 1,000 kilometers away in the space, and let us now talk about taking it from 1 million kilometers away. So this is the scale when which we are talking about in case of semiconductor transistors. When we talk about 15 billion or 20 billion or 100 billion kind of number, these are the scales we are talking about. Just imagine, because this is what we see on the surface of our planet. 1 meter, 2 meter, these are dimensions which we can easily resolve or we really understand. But when we talk about the dimensions in the scales of order of 3, 6, 9, this is what the scale is. So just imagine these are the kind of dimension which these transistors are fabricated at inside a chip. Okay, this is what we are looking at that from the top. Now let us see if we want to zoom in to the body of a human being. So how things will appear. So this is how. Let us, if we focus on the hand of this human being, if we zoom and let us say we have a very high resolution micro, and we zoom into the hand of this human being, and we move into the scales of millimeters. So this is what we will see at the surface of skin of this man. Now let us zoom again, and we move to scales of 1 micron, and then we start seeing this nucleus of the cell inside the human body. And then if we again zoom and move to the angstrom scale, then we start seeing the building blocks of DNA. So you can understand like what are these transistors, how small they are, and this is what has revolutionized the whole industry, not only electronics, but it has played major role in affecting pretty much every other aspect of human life. Okay, so the idea of these pictures are just to kind of feeling like these are the scales, because it is easy to talk in numbers like billions, billions, but it doesn't, we do not like easily correlate to the kind of scales we are talking about. Okay, so next point which I want to emphasize is just think about this number 1.3 into 10 to the 22. So this is just an estimate. Like if we talk about the whole number of chips which has been fabricated since the VLSI or semiconductor revolution, last 5 6 decades, and every year, if you want to see like how many transistors have been fabricated, so this is the number. Okay, so these many number of transistors have been fabricated till now, and there is an estimate like these are the number of stars in the universe, 1 into 10 to the 22. So it can be easily interpreted like there is nothing else which the human beings have manufactured on this planet which matches the number of transistors which has been manufactured till now. Okay, so just understand like this is the MOSFETs are the most manufactured item of all time. Nothing beats that. Whatever you can think about, you talk about nails or automobiles, cars, soaps, whatever, because these are all manufacturing industries. These are manufactured products. So nothing beats the number of MOSFET which has been manufactured. So these are the quantities uh, we are referring to. And what is the transistor? So this is a typical picture of a transistor. This, when I talk, this is the most manufactured item by human beings. This is how a transistor looks like. This is basically a FinFET transistor. Okay, this is what has driven. This is the engine of growth of electronics, semiconductor. Maybe what I should say is like humanity right now. And how these are manufactured? So these are the machines. These are the kind of machines which are used inside a foundry or a fab. So this particular machine is the one which has been talked about nowadays a lot. This is a lithography machine from ASML, and each machine costs around maybe 200 to 300 million dollars. And most important aspect about this machine is like nobody else can manufacture it. Even ASML took the research of around 2 decades to basically arrive at the latest lithography machine, which is being used right now in the leading fabs of Intel and TSMC. Okay, and nobody, no other company can manufacture it. Okay, and this is one reason why there are so much political talk going around the world. Like you must have heard, like India, US and China are fighting chip war or semiconductor wars. The China is developing their own domestic industry, and US wants to strangulate them. So these are the kind of equipment which play a major role behind the scenes, because if a country does not has, or if a leading fab does not has access to lithography tool, they can do nothing. Another thing about this is like it's very complicated. This is one of the I should not say one of the, I think this is the most sophisticated piece of engineering which is being built by humans right now. And only like 20 to 30 machines are manufactured every year. So it's not like you can build it as per the will of the manufacturer. And where are these machines fitted? These machines are fitted inside a fab. I think pretty much everybody you know about. TSMC is the leading fab in the world. It's not like one fab; they have multiple fabs. This is a picture of their Fab 18, and a leading edge fab typically takes around like anything from 15 to 20 billion dollars to that's just to set up the fab, and to run it and to get the output and yield out of it. It's another piece of process which is required inside the fab by the fab engineers. So it's a very very like cost incentive field, I think. And like India has also has its fab SCL. I think you know that's the only fab right now which is working, and Tatas are coming up with their own. But it's very very difficult. Like fab business is very difficult. It's not easy to set up a fab, to basically make everything work properly, to uh, gain the yields which are required from the fab. Okay, but then it's necessary because semiconductors are way of life nowadays. So it's very important. Like every country, they have their own fab, especially a country like India, because we are an aspiring nation. We cannot be left dependent on outside uh, basically suppliers to supply the basic components which goes into pretty much everything which we are using nowadays. Okay, so this is a bit of context about the current history. So it's a very important. Like if you want to understand where you are right now, we need to see where we started with. Okay, so let us go a little bit, not little bit, like 6 7 decades back, how this whole semiconductor revolution started. Okay, so this is a picture from 1944. This is a computer, leading computer. In fact, this was the leading computer at that time. It was called ENIAC, and it was used by US for World War II. And its purpose was to basically determine the trajectory of projectiles or missiles which they were launching at that time. So I think you know, like pretty much all the state of the art technologies, they are born from the defense industry. So this is one of the examples. Okay, and inside it there were around 17,000 tubes, because there were no solid state transistor at that time. So the transistor which were there, they were basically kind of glass tubes. They had anode, cathode kind of terminals, and there was a gate terminal, but everything lies inside a glass tube. So they were called tubes. So this is an example how those transistors looked at. They were bulky, power hungry, and they also used to get heated up a lot. So they were not very efficient, but this was the technology of that time. All the calculations which were required in order to determine the trajectory of the projectile was based on, because everything needed some calculations, and these were the kind of devices which were running behind the computers at that time. But they obviously they were not very efficient. So the next discovery which was made was in the form of semiconductor material. The world came to arrive like there are certain materials like everybody knows about periodic table. There are number of elements there, and then there are conductors and insulators. So conductor is like if you apply a live current to a iron cable or iron wire or iron rod, you cannot control that current. That control will pass through that iron rod. Similarly, if you apply a live wire through a wooden plank, it won't pass through it. So this is like the conductor is what it cannot control the flow of control. If current is flowing, it will flow through it. A wood will not allow. An insulator will not allow. So the world got to know like there are certain elements and they have a property like the current through them can be controlled. If you want to stop the current, you can do that. You can make the current to flow, or if you can also control the quantity of the current. So those were the new class of materials which are called semiconductors, and primary among them was silicon and germanium at that time. And then people started working around them. They thought like, is there a way we can try to control the flow of current, the same thing which they were using with these vacuum tubes, and we can build some kind of an efficient device which will be used for future computation and other requirements. So that's what semiconductors came into picture, and this was around the same 40s decades. And then this was the first transistors, basically a solid state transistor, which was built in Bell Lab in 1947. Okay, so this is what it looked like at that time. And using that transistor in 1958, so it took almost 1 decade to arrive at an integrated circuit. So this was an integrated circuit which was built by I think Jack Kilby of Texas Instrument, and it was I think a phase shifter or phase oscillator, something that kind of a circuit. It had a transistor and few resistors and one capacitor. So this was a basic first integrated circuit which was built in 1958. And then people started adding more and more devices, and this was the way at that time the masks were prepared. So nowadays we have billions and billions of transistors. So there is no way we can build, like basically print the features of a transistor or other devices on a silicon with semiconductor material using these manual ways. But this was the way. Whatever features needs to be printed on a silicon material or semiconductor material were basically carved out of this rubylith sheet, and then light was passed out of it. It used to basically act as a mask. So that was a kind of the way which this industry started. And then this is the first basically commercially available integrated circuit. It was in 1961 from Fairchild Semiconductor. It is a three input NOR gate. Okay, so this you can say is the first commercially available integrated, like which was available for people to build their circuits around at that time. And then I think this journey started. Basically, it exploded with every decade. The number of transistors started like the on the same piece of area. It started increasing many folds. You can see how this progressed. Okay, from just single or few number of transistors to millions, and now the billions transistor in same unit area. And with that started the journey of like lowering technology node. I think everybody knows about like a 130, 180 nanometer, 2 nanometer, 5 nanometer. So this revolution started with it. And there was a big role played by Moore's law, the Gordon Moore, who was one of the founders of Intel. So in around 1970s, he predicted like the way the semiconductor industry is progressing. He plotted like a graph where he put like how many transistors are getting printed on a same piece of uh, die area, and he came around a conclusion like in every 18 months the number of transistors which can be imprinted because of the basic evolution of the technology. And when I say technology, it talks about the fabrication technology, the manufacturing, because this revolution could not have been done without the effort which the fab engineers and scientists played, because they were the one who basically controlled how the shrinkage of transistors and other elements started take place inside a fab. So Gordon Moore arrived at a conclusion like in every 18 months, he predicted like the number of transistors will get doubled on a same area. So okay, so that was how the Moore law came into picture, and then the industry took that law as a like a kind of what you can say reference for them. So every 18 months, there was a race, like who will come up with the latest technology node, and they will try to double the number of transistors, and accordingly, the node size kept on shrinking. And when I talk about node, at that era, this node was decided by the channel length of a transistor. It was a MOSFET, like how smaller the channel length you can make, because the smaller the channel length, the smaller the size of an overall transistor, and also the speed of transistors getting doubled. So these were the two parameters primarily which drove the progress of this industry. Like they wanted to small do the smaller transistors and increase the speed, and we also with smaller size the power dissipation, power consumption of a transistor also reduced. So these were the parameters which drove the success, and also the backup given by Moore's law. So yeah, here you can see the number of transistors, how they keep on increasing exponentially every like 2 years, 18 months time period. Okay, yeah. So this is one important conclusion. So, like, if you consider like from the timeline around 1960s to 2020s, if you want to just see like how much the electronics or semiconductors have evolved, just imagine like the kind of automobiles or cars which were available in 60s decades. So a typical or the fastest speed which could be attained by a car in 1960s were around 274 kilometer per hour. And in 2020s, I think this speed became almost double, but nothing much, like around 500 kilometer per hour. Similarly, because of all the evolvement in other technologies related to mechanical and automotive, the fuel efficiency obviously increased because we came across lighter materials which were used to manufacture the car bodies. So obviously, I think that the fuel efficiency of a car, typical car, increased around 3 times. But now let us imagine, like if the progress in automotive industry would have taken at the same pace as Moore's law did in electronics or semiconductor industry, what could have been the numbers? Just imagine. This is not a realistic apprehension, but just to take an idea like how much electronics have progressed. Okay, so if the progress in the car technology or automotive technology had taken place at the same pace in which the semiconductors have progressed, so this should have been the speed of a car. It is much more than the speed of light, so it's not possible practically. And this could should have been the efficiency of a car. So just imagine like how much efficient the electronics has become. The transistors, which are the prime basically motivator of this revolution, if the transistor would not have shrunk so much, if the number of transistors which have been put in the same die area, unit die area, would not have increased multifold, this kind of benefits which we are seeing today would not have been possible. Okay, so this is not a practical, but just to give you an idea, if we want to compare like the electronics industry, how it has evolved vis-a-vis the mechanical or electrical or some other domains. So this basically conjecture gives you a good idea about that. Okay, so this was all about just to give you some motivation, like what are the field which we are looking at, because it you should also get an idea, like when I'm working in a semiconductor or electric demand, what are the things which should be motivating me. So I hope this keeps you motivated about the work which you will be doing further. And as part of this boot camp, we want to these are the steps which you want to do. So primarily, this boot camp is oriented toward analog design. So I will not be talking about digital design here. This is primarily analog design, and we also talk about analog design, custom design. Why custom? Because this is basically handcrafted kind of a thing. You do not do most of the things manually. You have to do all the things physically by your hand, like whatever things you build, they have to be done customly. Like whatever schematic you are doing, whatever layout, other steps you are doing, they have to be done by hand. So there is not so much more automation available in analog design as in digital design. So yeah, so we will start with schematic and then simulate the circuit, then convert whatever schematic has been done, whatever the electrical architecture has been selected. Then it for manufacturing it inside a fab, it has to be converted into physical layers or mask layers. That is the process which is done then through IC layout, that we will look into it. And then it's not like you have done your schematic front end design and you have done your layout and you can send it your design for fabrication to a fab. It's not like that. So there are a lot of verification checks which need to be done on your design. We will understand about them, why, what are they, and why they are required. And then yeah, so the big deal about this is like uh, we have a time period of around 17 to 18 days, because this shuttle will be going in the first week of May 2026. So by that time we have to complete, basically you have to complete a design, and one of the designs which is fully completed, which goes through all these steps. And if there are multiple steps, then we will have to adjust one of the designs, which will be sent for fabrication using the tiny tape out shuttle in Skywater 130 nanometer. Okay, so the idea is, you will go, I will basically teach you these steps, what are the tools which are required, how to run these steps, and you will select one circuit which you will try to go through these steps. You will complete it, and by the end of this month, around by 30th April, you should be ready with your design. So, and that design has a good chance of getting fabricated, and then 3 4 months later, when the fabrication is done and boards are received, you will be able to basically test your circuit on that. Okay, and one important thing is, because we have a very small time period, and also there's a limitation number of pins which are available in this shutter. So I suggest you take a very small design, practical analog circuit, which is you are really able to do in this time duration of 17 18 days. So you can take a small analog circuit like an op amp, a two-stage op amp, a Miller op amp, which has a two inputs, one output. So three pins are required, or maybe a band gap reference. So these four pins are analog pins. VDD and VSS are excluded from it. So these four pins you can use for your four and whatever inputs and outputs you required. So these are the examples, op amp or band gap reference. But if you have any other thing in your mind, you can please do that also. Just try to keep a small circuit so that you are able to complete all these steps. We do not want like you put lot of effort and at the end of it you are not able to complete it. So just completing it, the complete flow, designing a circuit and able to do a GDS is in itself a big deal. Okay, so just try to keep a small circuit. And if you need any help in selecting any circuit, you can please contact me on Slack. I will be able to ready, like happily available to help you there. Okay, so in order to do our this bootcamp, what we need, we will be using only open source softwares and a PDK, which is open source is from Skywater. So there are no commercial tools or softwares used here. Okay, no Cadence, no Synopsys, nothing. So these will be all open source software. A good thing about open source software, they are free to download. You need not pay any money to anybody for them. They are easily installable. Although they have some challenges, because if you're new to Linux ecosystem, people generally face some issues. So that's why we have given you this Docker, because everything gets pre-installed here. You need not do anything manually. Yeah, and no NDAs are involved. Okay, so these are the benefits. At the end of this bootcamp, whatever design you do, it will get fabricated and it will package inside this kind of a QFN package. So your design will be among lot of other designs, because tiny tape out is not like it's only your design. There will be hundreds of other designs, and your design will be one of them. And but you will be able to basically lock into your design inside this chip and test it. Okay, and in order to do this testing, there will be a test port. This is a very good thing which Tiny Tapeout team has done. They have made a very good infrastructure where the people need not worry about like how will they test their designs, because I have seen a lot of people, they do get their design fabricated, but at the end of a shuttle, what they get in their hands are dies, bare dies. And then it is another challenge to get those dies packaged inside a package, then build a test board around this package, then mount that package onto a test bed, and then you are really able to do testing of your design. So not only it takes a lot of time, but also a lot of resources and headache is there. And at your stage, at academia students stage, you do not want that kind of like infrastructure hurdles to be presented to you. So Tiny Tapeout gives you this test board mounted with a chip, and there are pins available, and these can be easily tested using a typical standard measurement infrastructure like VCOs or power sources, whatever is required. Okay. And yeah, and at the end of thing, the big the credit or the claim which you can do, if you are really able to go through this whole process and able to test your design, you can proudly say like I have a silicon proven design. I think just to from the like career perspective you are talking, or if you're going to some interview or somewhere, if you just say them like, I have designed this, let us say it is just a small op-amp, I've designed it, I've got it fabricated, and I've also tested it. I think nothing beats that kind of experience. Okay, whatever uh, is the like background of your interview or whoever you are talking to, I think that kind of benefits it, this basically is being presented through you, this boot camp. Yeah. So yeah, I think that's all for this. Maybe now,
Yeah. So the participants, do you have any questions or something?
yeah, maybe if you have till now, if you have any question, you are most welcome to ask. If anybody has any doubt, like how to select a circuit or what you want to do with analog design, anything else.
Sir, I had one doubt regarding the pad ring and IO pins. So, like you said, there were a limited number of IO pins. So, how
Hmm.
would that affect our layout or our design? As I have not heard about them, I just wanted to get some background information.
So please note, like in this case, you will not be directly accessing IO pins, because this is part of a tiny tape out team. They have a pre-designed chip in which there is an empty area. All the IO pins are around that periphery of this chip. So what you will be getting a four connections, basically kind of a metal pads. And whatever circuit you are building, you have to connect your inputs or outputs to those four metal pads. Okay, and those metal pads in turn will be connected to the IO pins, and those IO pins are basically multiplexed. They are multiplexed between multiple designs which are available in inside the tiny tape out shuttle. Okay, so as a designer, you just need to care about your design. Like if you are building an op-amp, you just need to care about your two inputs and one output. So you will be having four pins. You can use them as required as possible. If you want to use two analog inputs, you can connect two analog inputs to those two metal pads, and then one output pad can be connected to the output of your op-amp.
Okay, sir, got it. And I had one more question, like can we do the GM over ID characterization of the NMOS and PMOS devices? So we can get the
Yeah,
whole like
that can be done. I think I will show you. Okay, I will not exactly cover that point, but I will show you there are tools available. Have you heard about Xschem, Ngspice?
yes, sir, in the open source flow.
Yeah. So so main thing is the tools. So those tools are available, and using those tools, you can implement whatever basically idea you have. If you want to do a GM by ID, that's possible to do in it.
Okay, sir.
Yeah, Saili Sahu is asking difference between digital IC and analog IC. They both in
Yeah.
semiconductor material.
So, Shelly, as far as physical implementation or manufacturing goes, there is no difference, because on a semiconductor silicon wafer, everything is same. The way the analog, in fact, there is nothing like analog or digital when you talk about a semiconductor. It's only based on your application. Okay, if your signals are in digital domain, basically whatever your input is, it is in 1 0 digital signal format, discrete signal, and your output is also in 1 0 format, then that IC is called digital IC. If your if for example, if your IC receives an analog signal, let us say if let us say I am talking to you. So if I am talking, my voice is being captured in the by the microphone of this laptop. So there is an IC inside it which will capture my voice. It will convert into an electrical signal. That will be an analog signal because there are no 1 0s there. So there is basically amplitude or a frequency associated with that signal that will go inside an IC, which will basically do a signal processing. So that IC is basically analog IC. Similarly, if there is a microprocessor inside this laptop, then that is a digital IC. But from manufacturing point of view, there is no difference. Is RFIC design a part of analog design, or is it a complete? No. So RFIC design is a one level above analog IC design. Okay. So you definitely, so there is an RF design, MMIC design, where you use discrete components to build your RF circuit, basically the wireless circuit which work in RF domain. But in RFIC design, we are using the semiconductor devices which are available to us in normal CMOS process like MOSFETs, capacitors, resistors, and one important element which gets added into RFIC design is inductors. So everything is on like a silicon material or CMOS technology. If that technology is used to build RF circuits like LNAs, PS, transceivers, or receiver, then that is called RFIC design. So in a way, if I like summarize, RFIC design is a branch over a typical analog IC design.
Yeah, you can use any of the tools. I would like to add like Xschem or eSIM. eSIM is made by us by the FOSSEE team. So
Yeah.
yeah,
No, I was telling like if you are well versed with eSIM, I think I encourage you to use eSIM because I understand that Sky 130 PDK is also integrated into eSIM. Okay, so it doesn't matter like whatever the tool you use for front end design, you can use because for backend we just need the netlist. If that netlist comes from eSIM or Xschem, I think that is independent of it. Okay, so now let's actually go into what our theme of this bootcamp is. Maybe I will just give you a bit brief idea about what analog IC design is, and then we will go into actual tools. Okay, so this is what our agenda for this bootcamp is. We will learn the practical design steps of analog IC design. We will start with schematic, build layout. That then, if your design is selected, it will get fabricated into a package. That package will get mounted in test board, and this is what will be you will be getting. And okay, so this is what are the typical requirements of IC design. You need a foundry access, a fab, where the designs will get fabricated, need a PDK, the technology based on which the designs will be done, EDA tools, and then IPs also. If you are doing very complex designs, you do not start everything building from scratch. If there are some IPs which are available, they are designed by somebody else, you buy them and then integrate into your design. And obviously you need a design team. It's not like a single engineer will be able to do a complex IC. If you're doing a small block, it's okay, you can do alone. But if you're talking about building a mobile processor or doing a high-end ADC or DAC kind of a circuit or RFIC, you need a group of team, like experienced teams who will be able to collaborate and perform different steps. So these are the basic. This I'm talking about a typical industry setup. Okay, I think you should have an idea like what exactly are required. And once everything is done, this is an AND gate. Get access to a practical ASIC at the end of it. As far as technology is concerned, in this particular case, we will be using Skywater 130 nanometer. PDK is a process design kit. Basically, whatever processes are used inside a fab, the physical processes, lithography, diffusion, etching, metallization, those are the practical things which are done on a silicon wafer inside a fab. All those steps are captured inside software files, which are basically then used or passed on to a designer. Based on that, he designs his circuits for that particular technology and fab. So it's very important to understand PDK. And then Sky 130, this is a typical name. Like in this case, this technology belongs to Skywater Foundry and 130 nanometer technology node. Okay. So what is PDK? It's if you are IC designer, it's very important you understand PDK, and especially if you're an analog IC designer. I think digital designer, even if he doesn't go into detail of a PDK, it's okay for him because most of the heavy loading is done by the tools. As I mentioned, pretty much everything is automated there. But for an analog designer, it's very important to understand your technology and PDK. So inside PDK, there are different steps which we'll be covering later: schematic, layout, everything. And according to each step, there are different files which are available inside a PDK. There are symbols, callbacks which are required by symbols and P cells, netlisters, spice models, everything. So it's not like you need to be master of these things, but you should be aware of these things because whenever you are getting a new technology or a new foundry to work on, the first interaction for a designer will be with the PDK. Okay, so it's very important that you understand the structure of a PDK, where which file lies where and which file is used for which purpose, so that you are well versed how to do your design because it makes your design flow or design step easier later on. Okay, so these are like typical integrated circuit. In order to design it and fabricate it, you need EDA tools. You need a concept like what circuit you want. It can be in form of a RTL or a netlist design, and then you need a PDK data. It's only then you will be able to do your design or start your design. And inside a PDK data, you get all those things, libraries, the spice models, the standard cells for digital design, And then there are different kind of rule decks which are required for DRC, LVS, parasitic. All these things are available. And this is what a typical technology stack looks like when our devices, or when you talk about any specific technology, like this is Skywater 130 nanometer. So they have their own kind of a stack of whatever layers are used in it, and how to realize the transistor, NMOS, PMOS, what all the different fabrication layers are there. And then these are called front end layers because these are basically fabricated or manufactured inside the surface of a wafer. So these all these the transistor is basically realized inside the surface of a wafer. That's why these are called front end layers. And then whatever things are basically fabricated or manufactured over the surface of a wafer, these are called back-end layers. So basically all the metallization layers or vias which are manufactured in order to make the connections between different devices, they are back-end layers. So for this particular technology, this is what we get for Skywater 130 nanometer. This is a stack up, back-end stack up. These are the metal layers which are used to make connections, the vias, etc. So mind you, all this information, if you talk about proprietary foundry or proprietary PDK, these cannot be published as per NDAs in public domain. Okay, these are very kind of a secretive informations which no foundry wants to be put in public domain. But because we are talking about open source and Skywater, and there are two other foundries like GF and HP, they have put these things in public domain. That's why we are able to discuss this thing, and these are actually available in public domain. Okay, so now come to the real flow steps. If I talk about an analog IC design flow, this is how a flow looks like. You start with a design concept. Let us say you start with a concept. I want to design an operational amplifier. Then you define it. By define, I mean like what kind of specifications you want, what kind of a gain you required, what kind of bandwidth, what kind of noise, slew rate, all those things. You define it because you cannot start building your design in dark. You need some reference based on which you will design it. Then start implementing it. Implementing this in basically you decide upon an architecture, because op-amps can be of different types. There can be a two-stage op-amp, there can be cascade op-amp, there can be folded cascade, or a high-speed op-amp, or low-noise op-amp. So you need to identify some architecture. So this is what I'm talking about. Typical case. You for this particular bootcamp, you need not worry about so much. I think whatever you understand, you start building upon that, because there's not much time to delve on all these aspects. First three aspects. Important step which comes is simulation. So whatever architecture you have decided, now you have a PDK, you have a target technology, you want to analyze your design. So you simulate your design in that particular technology using simulator. Then once simulation is done, so this aspect of a design is called front end design or electrical design, because till now you are dealing only on the front end aspect. You are not now ready with manufacturing of your design. So these are electrical design stage. Then moves to the physical design stage, where you convert your design, whatever circuit you want to manufacture, into physical layers, which will be finally implemented on silicon or wafer. So that's what IC layout stage comes. Whatever basically circuit has been finalized, you convert it into a layout where all the layers of transistors or resistors, capacitors, which are laid out inside a layout tool to realize a GDS. Once layout is done, then as I mentioned, you need to run some verification steps. So there are DRC, there is LVS, we will talk about it later. Then parasitic extraction, you want to check the effect of parasitics. Once everything is done, then a GDS is released. This is what we call as a tape out also in industry terminology. Once tape out is done, your design goes to fabrication inside a fab. It's again, I think this is out of scope and this is of our current lecture, but this is where everything from an idea gets converted onto a silicon wafer. Various steps are followed, and typically it takes anywhere from 3 to 4 months to get your design fabricated on a wafer from the tape out stage. Once the design is done, it's not like whatever gets fabricated, you can directly use it for whatever requirements are inside a mobile phone or a car, everything. It is because everything lies on a wafer. You need to extract dies from a wafer. That steps happens inside a ATMP unit, where assembly and packaging of dies from a wafer happens. Then testing is done, verification is done, and when your IC is passed, then finally it goes into a product. So this is what a typical life cycle of an analog IC looks like. Digital, I think pretty much every IC goes through this stage only, but the difference lies in the front end stage. Here we start with the schematic or netlist. In digital design, you start with RTL, and then there are different other stages like timing and other basically requirements through which your circuit is verified. So that's where the difference lies in. But otherwise, fabrication and testing assembly, they are basic kind of common steps for the basic realization of an IC from a concept to a product. Okay, so in our case, we will be using these tools, and these are the steps for schematic and netlist design. We will be using Xschem, open source tool. For simulation, Ngspice. For circuit layout, Magic layout tool. DRC is also handled by Magic Design Rule Check. LVS layout versus schematic by a tool called NetGen. Then parasitic extraction. I think this step we will be skipping for this bootcamp because it's not very much mandatory because the circuits are very small and I do not want to complicate things too much. So maybe if needed, we won't be doing parasitic extraction. Because I think it won't affect much the performance of your circuit. But if time permitted, we will definitely look into it. And then finally, once everything is passed, you have gone through this process, you have cleared your verification check, the tape out. Okay, tape out means you convert your layout into GDS and it is ready for sending it to fabrication. And as I mentioned, most of these steps are manual. Basically, you have to physically do these steps. Okay, so I will quickly go through this slide because we will practically looking at them. Schematic design. This is how a schematic looks like. This is an Xschem tool. From Xschem tool, there are two steps. You will be basically passing on this schematic to a simulator Ngspice in form of a netlist, which will simulate it. And then whatever results are coming from this simulation, you will be able to see it on waveform viewer. Then Spice simulation is done in Ngspice. So there is no GUI for Spice. This is a command line tool. You will see it in terminal. Basically integrated inside an Xschem. Whatever circuit is simulated, you will be able to see the what all steps have run and what is the output, whether the simulation is running successfully or not. If not, it will give you warnings and errors. Okay, once schematic is done, from schematic, a netlist is generated. There, that netlist is basically passed on to Ngspice here for simulation, and then that netlist is also used for converting your design into layout inside Magic, which is a layout tool. This is what is IC layout. Basically, IC layout is physical arrangement of whatever devices you have used inside your design. Like what if you are using op-amp, you are using NMOS, PMOS, resistors, MIMCAP, whatever, and the way they are connected to each other. So you have to convert everything into physical structure. So that process of converting your electrical design into physical structure by placing the components, right component, and make connecting them is called IC layout. And there are specialized tools used. There are specialized techniques also used for IC layout because once when you are doing a product level design, you have to take care of a lot of other things like matching and other things. You do not want like parasitics to be affecting your design performance. All those aspects need to be taken care. And generally, they are task of a specialized layout engineers. Okay, in industry, the role is very well divided. Like if somebody is doing front end design, he's generally he does not do layout design unless he is very experienced. Layout design, front end designer passes on his schematic to a layout designer, and layout designer is basically specialized in working in converting that designs into layout. So that's how it works there. Then design rule check. Whatever layout has been done, a foundry has requirements. They have their own set of rules based on which you have to place your layers, which will basically implement it into masks and then into manufacturing. So those layers has to be basically followed while doing layout. Those and there are specific rules for those. Like if they are you are using metal one, the metal one will have its rule. Like there should be minimum this much spacing between two metal one layers, and the width should not be less than this. Then vias will have their own layers. Then every layer basically has rules for itself, and then in relation to other another layer. So all those things are basically captured into design rules, which are provided by Foundry. And layout engineer basically has to respect those rules. He cannot go out of those rules. If you have done a very good, let us say you have done a very good layout, but you are having even a small error, even if a one error which Foundry is not ready to accept, then your design can be rejected. Okay, it's as serious as this much. So it's very important. Like even if you do a very good layout, you just keep a track of the what are DRC rules or violations you are getting. Okay, it's not like if you have done a complete layout and at the end you will try to look into DRC, because by that time you might have accumulated lot of maybe hundreds and thousands of errors, and at that stage it becomes very difficult to rectify those. So this is very important. Without DRC check, a boundary will not accept your layout for taking into fabrication. Then LVS, basically it is required because your electrical circuit is one thing and putting it into a layout is another thing, and you have to put the correct instances there, and their dimensions, the width and length which are used in schematic should be same, and also the connections which are made. If your layout, let us say you are using, like let us say maybe several instances or several devices inside your design, so there's a very high chance like while making connections you might make a wrong connection or you might forget a connection. So if such a thing happens, then obviously your layout is not representing the true picture of your schematic. Electrically, they are not same. And if you send that layout for fabrication, obviously it won't work because the connections are not proper. So this is that stage where you catch these kind of errors, layout versus schematic. You basically generate a netlist from your schematic, you generate a netlist from your layout, and then compare those. If those netlists are same or they matches, it means electrically your layout is equivalent to your schematic, and basically then the things are okay. Okay, so this is also important. Yeah, parasitic extraction, it is required because when I'm simulating my circuit in schematic, it's pretty much there is nothing, no physical layers use it. These are all, I'm working in a virtual space using just a model. But when I am implementing this schematic into a layout, I'm using metal layers to make the connections, and those metal layers have their own electrical characteristics. Like a metal drawn will have its own resistance, capacitance, or maybe inductance also if we are talking for RF or high frequency domain. And those values, parasitic values, which are not basically they are not intentional. They came into picture just because the way I have done a layout. They may affect the performance of your design. So it's important. Like I should be aware of that. Like these parasitics should not affect the performance of my design. Let us say I designed my op amp for 60 dB gain or 100 megahertz bandwidth, but due to these parasitics, my gain dropped to 55 dB or my bandwidth dropped to 80 megahertz. So that this is like I'm not meeting my specification. So this is not acceptable. So is that's where it is important to do a parasitic extraction. But in this case, because we are focusing on very small designs, and I do not expect you to be doing a very complex layout or using very wide or big metal lines. So I do not expect parasitic extraction to play a big role. So we can avoid this step. Yeah. So yeah, so that's all. So this is the summary: Xschem for schematic and netlist, and Ngspice for simulation, Magic for layout, and netlist. So these are the four tools which will be used, and these four tools are already pre-integrated inside the Docker container, which has been shared earlier with you on Slack. So you need not go through the pain of installing these tools. Everything has been done, taken care of you. You can straight away start using these tools and building your design, the way which I will be covering next. Okay, so this I will show you. Yeah, so this is the first step which we'll be looking at today: schematic and simulation. Then circuit layout and DRC maybe we will look at tomorrow, and then the other remaining steps we will look at on Monday, the last lecture. Okay, so I will quickly go through this. This is how a scheme looks like. These are the commands which will be used. These commands I will be sharing with you, so don't worry. These will be used. I will practically show you how to use them. Then we will be building a schematic, converting it into a symbol, and then that symbol will be used in a test bench to run a simulation. And these are the steps which we will see next. Code block, everything I will show you. So maybe I can skip these things quickly. And now let us move directly into our tool and start building our design. Okay, so once you have installed the steps following the document which have been shared on Slack, this is the screen you which will see, blank screen, the Linux environment. And now let us start from here. I will open my terminal, and okay, so now please note this down very carefully. Whatever designs, whatever files, schematic, everything you will be doing will be inside this folder, design data. Please don't build anything or save anything outside of it, because because this is a Docker image. In case if we update it or if it gets corrupted or somehow it doesn't work, whatever that design data you do outside of this file will get lost, but whatever things you build inside this design data will get saved inside your Windows environment file structure. Okay, so this Docker has been built like that way. Even if something happens to this design, your files will remain safe. You can anytime use it later in open source tools that is easily accessible to you. So please note, please build do anything inside this design data folder. Okay, so I have moved into design data, and the first thing I will do, like, let us say I want to make a design. I will make my design folder. If it is an OPAMP or whatever, this is my design. Okay, it already exists. I will make something. Test design. Okay, so this has been created, test underscore design, and I will go inside it. And next important thing is I will make three different folders. One is for Xschem. All my schematic related things, whatever schematic, test bench, simulation, everything will lie inside it. Then I will make magic. The layout, whatever layout I do, files I create, they will reside inside this magic folder. And another is NetGen. This is for LVS. Okay, so whatever LVS I do will be run inside this folder. It's although you can do everything inside a single folder, but there are so many files generated during the IC design flow. It's a good habit to keep them separated, like based on the design step or the tool which you are using. Okay, so this is a kind of uh, good habit which I suggest you should follow. Okay, so these three folders are created. Now let us, because our today's task is to build a schematic, so I will go inside Xschem and I will launch Xschem. You just need to press Xschem ampersand, and this Xschem tool will get invoked. And also, not only tool, the PDK has also been pre-integrated inside it. So you need not worry about all those steps, how to because they are little bit tricky. So we have taken care of all those things. So you just need to do this much and Xschem will get invoked. And the first screen which you see is very important because this is a good part of open source ecosystem. Actually, they have provided all the information about PDK devices, test bench, everything on this main sheet. And this will be a very good reference resource if you want to learn about any other steps, kind of analysis you want to run, or you want to see any examples. You can just click on these and they will be available and what kind of devices are available, and another any other resources. So this will be kind of your go-to place if you want to if you are stuck somewhere. I think there are a lot of examples available here. You can go inside them. Let me show you. Just click it and press this down arrow button and you will get inside those examples. Okay, and then there are GitHub repositories also. You can click them and they will open. So this is a very important reference point to start with. Okay, now let us start building our first schematic. I will press this plus button, a new sheet will open. And I want to, okay, so there's an option to change the color. I generally prefer to use it in white. So I will start building one small amplifier, a common source amplifier, as part of this bootcamp. I will show you how to build a schematic of it. For that, I need to first access my PDK library where my devices are. So for that, I will press Shift I on my keyboard. Don't worry, I will share this command with you on Slack. So this kind of window will open. And this is my Xschem PDK library where my PDK devices are available. And the primitive devices are there are different other libraries also in this PDK library, but I am specifically looking at primitive devices. And so here are my primitive devices which are as part of this PDK, different kind of NFET, PFET, and resistors and capacitor. All those are available here. So today I will be building a simple single stage NMOS common source amplifier. So let me take a 0.18 NFET symbol. I will select it, place it. Now, if I want to zoom, see the full screen, press F key on your keyboard. And this is how this symbol will appear. So I have placed this symbol. Next, I want to place resistor. Again, Shift I and there are different kind of resistors available here. So let me take this particular resistor. Okay, one important thing, if you want to learn about these devices, so this whole documentation of Skywater PDK is available online. You just type Skywater open source documentation. You will be able to understand the properties, whatever parameters are associated with device. Everything is available online. I will place my resistor. Okay, so these two components have been put. Now I need to connect them. So for connecting, bring the cursor on the terminal and press W key on the keyboard, and the wire will start. Take that wire to another terminal and just press the left mouse button and the wire will stop. So this is how you do start doing wiring. So let me quickly do wiring for other. W to the wiring, short the bulk and source terminal of NMOS, and full screen. Okay, so this is the devices have been placed, the terminals have been connected. Now I want to place the pins terminals. Basically, I want to identify what is this terminal input output with. So for that, I will be using pins. Again, press Shift I, and you will go here. And in this case, because pins are generic components, they are not part of PDK, but they are part of Xschem library, because Xschem has its own library for default components like sources, etc. So this is the place where you will see those devices, Xschem devices. And I want a pin. I want to put a pin that is a default component. So I will look at a IO pin. It is called IO pin. And if I want to rotate this pin, Shift R key. Again, Shift R, copy. For copying, just select it and press the C key on the keyboard. Okay. Now, in order to name them, just double click and you can change the name VDD, PSS, out, INP. Okay, so these are the pin names, and now there's another terminal. There's a bulk terminal which is connected to the substrate of this poly resistor, and this has to be connected to VSS. So basically, this has to be connected to VSS. Either I can draw a wire from here to here, but another option is to just label it. Give this net a name which is same as VSS. So for that, I will again go to this Xschem library, default library, and I will label this wire. Okay. And VSS. Okay, so this is this is a very small primitive circuit done. So these are the steps till now. I basically instantiated the component from PDK library, put them here, and then connected them through wire element. Once wiring is done, gave them the names, different names, the pins, terminals. So this has been done. And now if I want to change the properties of this component, because that's a very important part of design. You want to basically design your circuit as per some specific gain value or something. So you have some values in my mind. So let us say I want to give this is a 2 kilo ohm resistor. I want to make it 1 kilo ohm. So I will change the length of this uh, resistor 3.5, and then you will see this resistance value will change here. Okay, I want to keep it as 1K. Maybe I will give it as 0.8. 0.7. Okay, so 992. So 1 kilo ohm, around 1 kilo ohm. And I want to change the width of or length of your NMOS. So this is where you can change the width. So please remember, do not put micron units, because this is what I have seen a lot of people do. They put a U micron unit around the dimensions, because the PDK is designed in such a way like it automatically converts these numbers into micron. So you just need to give the absolute value here. So let me give 30 here, and length is 0.25. Okay, so just because in analog design you just need to change width and length of a MOSFET, you cannot change anything else. So this is what I've done. So this has been done. So let us say this is my schematic which has been completed. I want to save it, file, save as, and I want to save it inside this Xschem folder. Please remember it, because this is the intention which we started with. Okay, I need to name it also. So I will give it a name of CS underscore amp. Okay, so this is my schematic done. It has been saved inside my Xschem folder. And next step is next I want to simulate it. So there are two ways to do it. One is I can start adding sources and all the simulated related elements inside this schematic itself and try to simulate it, but that's not a correct way to do it. So ideal way is to convert this into because this is just one component. Maybe you are doing a very complex design where different blocks are required. There may be, let us say, 10 or 12 different blocks are required. So you do not basically integrate all the schematics into a single sheet. You adopt a approach which is called hierarchical design. So we convert this schematic into a symbol, and then that symbol is used inside your top level schematic or in a test bench. So that's what we will adopt here also. I want to convert this schematic into a symbol. That I can do going to symbol and make symbol from schematic, this command. So if I press this, do you want to make a symbol? Yes. And this symbol will be created inside the same location where the schematic is. So I will just check it. Open new sheet, open. And yeah, so this is that symbol which has been created by my previous step. Okay, I will open it, and this is how this symbol looks like. So just see, these are the pins which has been automatically generated based on whatever pins we have generated here. So these symbol pins are here, but this symbol does not look appropriate to me because I want to align these pins as per my wish. I want to put VDD VSS on top and bottom. So this I can do by selecting these pins and move. For doing move, you need to press M key on your keyboard and then rotate Shift R. Okay, so one more thing. Since this is an amplifier, I do not want to give it a shape of a box. I want to make it look like a amplifier symbol. So I can also do that by moving this term, basically lines here. I can give it a shape of an amplifier. Okay, if I want to Shift R to rotate. Okay, so now this symbols looks pretty much okay to me. Like this is what I want it to represent in my test pen. Once it is done, I will save it. So the first step was I built my circuit schematic. This is what schematic. Then next is symbol. Now is the step where I want to simulate it. Okay, so this was my schematic design step, and now I want to simulate it. For that, I will open a new sheet. That will be another schematic sheet. Here I want to include this schematic in form of a symbol. I want to include here. So again, I will do Shift I, and I will go to the path where this symbol exists. I will select this symbol and instantiate it here. So please understand. So these are now three different sheets. Okay, so let me first save it by a different name so that you can understand it, because I have seen people make mistake here also. They get confused between the schematic sheet, the symbol sheet, and the test bench sheet. So let me save it by the name of a test bench. So this is cs underscore amp, and but it is a test bench. It is not a schematic sheet. So I will name it as a, let us say I want to run a sino transient analysis on it. So I will save it as a tran. Okay. So these are now three different sheet. This is my primitive schematic. This is the symbol of this schematic. And this is the test bench schematic where I now will now start putting all my sources and inputs, everything. So this is where I will make a setup for my simulation. So let us start building. I need to first attach the VDD and VSS to it. So again, go to my shift I, Xschem library. I look for a sources component, voltage source here. This is my voltage source. I need a ground symbol. Okay, so I will make a connection. This is my power supply, and this will go to ground VSS. Okay, and because this these are my 1.8 volt transistors, so power supply will be 1.8. So let me make it here also. And next I want to attach a input. Okay, so this same source element will be used here, but I will be giving a different kind of input to that, because I need to give a sinusoidal input. So I will make a specific change here. Okay, so this amplifier also needs some load where that output will go. Maybe it will be driving some other stage. So in order to represent that load, I will be putting some kind of a small load capacitor here. Let me put a capacitive load here. And this load will again have negative terminal connected to ground. Oh, okay, so anybody has any query till now? Okay, so let me continue then. So this is how my test bench looks like. I have given all my input sources, everything, power supply. Then comes few important steps, because this amplifier which has been built here, and okay, so from here you also can go inside the symbol and see your schematic like this, pressing this down arrow button. If you want to go back, you can press this up arrow button, and you can move back to your test bench schematic. Now, if you want to basically simulate it, and you are using a Sky 130 devices here, because these devices, NMOS and resistors, are specific to Sky Water 130 nanometer PDK. So you need to give them this test bench, the models, SPICE models, based on which this simulation will take place. So in order to get those SPICE model, again, as I mentioned at the start, this is the reference for you. So there is a symbol here. You just need to select it, copy it, Control C, and paste it, Control V. Okay. So this basically component has the path to those model files. Everything has been pre-coded into it. You need not do anything. So those models are now initiated inside this test bench. Okay. So this is one important part. Next is I want to give some commands, basically what kind of simulation I want to run. I need to give it, like I want to run a transient simulation, I want to run a DC analysis, or what is the time period for which that simulation should run. Okay. So for these things, I need to write some codes here, some commands. So there is a specific syntax for that. So that I can do by instantiating a code block from Xschem library. So there is a code block here, code underscore shown. You need to place it here. Okay, and need to write some commands here. So right now I am just, because I remember those commands, and but sometimes I also forget, but I will just be writing them here blankly. Or maybe what I can do, I can copy it from rather than doing it, saving some time. I've already built that. Let me copy it from my other test bin. Okay, let me try writing it here. So there is a specific meaning to all those commands. It will take a lot of time to make you understand it here, but I suggest I will share with you the links of these manuals, because if you want to uh, learn analog designs, you cannot get away from basically reading these manuals of these tools. So it's a good habit to basically understand these commands, what all is being run here. So first I will run an OP analysis. So, or for what you can do, I think for this boot camp, or for the whatever circuits you are trying to run, you can simply copy whatever I am doing, because this will be sufficient enough for doing simulations of your circuits like op amp, band gap, whatever analog circuit you are building. I think these commands are sufficient. But if you want to learn more about them, because if you start going in deep into it, because these will not be sufficient, you need much more to understand. For that, I advise strongly to get access to the manuals. These are available again online, or maybe I will also share the links to you, where you can pretty much understand what all these commands mean. Okay, so this is the basically this command tells what it tells is I want to run an operating point analysis, because I want to check the bias points of my components. What is my input voltages, and what are the voltages which are generated inside it. For that will be run using this OP analysis, and what it does, it will save whatever my data is generated inside this raw file. This is an output file from which that information will be annotated on this schematic. And then after that operating point analysis is run, then transient analysis can be run, and again that data will be saved in same raw file. But in order to avoid overwriting it, what we do is we use this set append write command, so that this overwrite does not happen between operating point and transient analysis simulation. Okay, so this append write should come after this. So this is very basic analysis. So we have done. Okay, one thing which is remaining is I need to name these wires also, so that it is easier to see the output waveforms, etc. So I will label them. Okay, so I think this is done. I This is my test pen schematic. These are my model files, Spice model files, and this is my syntax or my command based on which I want to run this simulation. Okay, so everything is run. Now I want to okay. One important thing, beside this schematic, all this information will get captured inside a netlist, because that netlist is a code which gets passed on to a simulator like Ngspice, and then a simulation is run. So in order to convert this whole this setup into a netlist, we will press this netlist button. It's very important. Okay, one more thing. It's important to set this step also, netlist directory. We want whatever steps or whatever has been run in this simulation, that gets saved inside a specific path or folder. And that path or folder I would like to create here. This was my Xschem folder. Yeah, I will make a directory called simulation here, and whatever Xschem simulation data will get saved inside it. I will set a path here, set netlist directory, design data, test design, Xschem, and simulation. So this is important. Please set this step also, netlist directory. And another step one needs to be added is here, create this fat.save file. So what is the significance of this save file? Basically, it will enable, if you want to see internal parameters of your NMOS, like because generally in analog design we want to see what is my VTH, what is my GM, GDS, all those, and parasitic capacitances. If I want to see these kind of parameters, so the developer has made it very easy. Like earlier we had to type these command manually here in order to get this kind of information, but now using this option, this file will get saved here, and we just need to include the path of this file. Okay, so now we can see this is the path where this file gets saved. We can also see it in terminal. Yeah, so this is the file which got created when I ran this command, but I want to add this file into my test bench. For that, I need to include it here. Just do this. And okay, so I think now pretty much everything is done. Now we will generate a netlist. Press this netlist button. If you want to see the netlist, go to simulation and press this edit netlist. And this is the netlist which get generated from your test bench. Okay, so this netlist, let us just quickly review this because it's very important. Please do make a habit to go through the netlist and understand it, because a lot of errors which are faced, they can be easily caught if you are able to read your netlist. So this is my sub circuit. This is my schematic or symbol of my main circuit, common source amplifier. This is the definition of NMOS. This is the poly resistor, and then this is my model file from the PDK based on which the simulation will be run. This is that save file which will basically include the operating point parameters, and this is my simulation control, where I mentioned what kind of analysis I need to run on my schematic or test bench. And these are the sources. Okay, one important thing which is missing is I have yet not defined my input source. It is still showing DC voltage, but I want to run a transient analysis because I mentioned, so I need to apply a sinusoidal source inside or a time varying source. So let me do that. Okay, so how I can do DC 0.9. Okay, so this is a specific syntax for sinusoidal source. So okay, let me show it you in schemat netlist. So this has been changed. I have saved it again. Now I will again regenerate the netlist, press netlist button, and the netlist would have got updated. Okay, so this is my input source now. Okay, yeah, I was talking about this input voltage source. So this is a syntax, DC voltage, sinusoidal voltage, and this is my like DC voltage, and this is my peak voltage of my sine signal, and this is the frequency of my input signal. Okay, so this is how I define my input transient signal source. Now let me try to run the simulation netlist and then simulate. Okay, so there is some error coming here. Okay, so I have given the wrong name of my save file, I think. Netlist and then simulate. So it takes some time to simulate this, and please wait for maybe 10-20 seconds, and it will give you the output. Yeah, so this simulation is run. So I think this looks pretty much okay. If there would have been an error or warning, that would get flagged here. Now, the next step is I want to see my whatever result has been generated from simulation on this schematic. For that, there are some small icons which can be used. So please copy these icons again from this top dot schematic. Copy, Control C, place on your test bench here, and this will help you to annotate your simulation data which get got saved in this raw file on those on this your schematic test bench. So first, if I want to see operating points, what are the node voltages generated, I will press this button. And how to do it, please note it, control key on your keyboard and left mouse button. If you press it, this will get updated, and these voltages got printed here. So you can see my DC voltage here is zero point 0.9 volt, my supply voltage is 1.8, and the output node voltage generated is 0.8793 volt. Okay, if I want to see inside this schematic, what got generated on my actual components, select it and go inside it, and you will see here also. So this is pretty much same. What all was because this got uh, basically brought outside the symbol, these voltages. So but you can see inside it also. If there are a lot of components there, so the DC operating node voltages you can see for all these components here. Okay, another thing was I wanted to, let us say I want to see the operating point conditions of like what is the GM, GTS, all those elements of my NMOS. So for that, I can add this component here, add effect param annotator here. And as you see, all those values were calculated already in my output raw file, and that those gets printed here itself. So this is a GM of my NMOS, GTS, VTH. So I think if you are in analog design, you would require these small signal parameters to be known to analyze your circuit if you want to calculate the gain or bandwidth. So this is how these also get generated from this operating point analysis. Okay. Now, besides DC analysis, I had already also run a transient analysis on my test bench. So I also expect to see my input and output waveforms. So let me see how can I plot those. So good thing about this tool is like you need not go to any external waveform viewer. You can just uh, add a waveform viewer here. Go to this simulation graphs, add waveform graph. Okay, and just double click on this, and here you can select what all nodes you want to plot, like INP input I want to see, add, and I also want to see out. Right. Okay, and these get added into here, and then if I press this again left, load waves. This is for loading waves only. This was only for annotating DC operating points. Okay, so just remember this. So now I press left mouse button, and these waveforms got generated on my this viewer. So now I can see this is my input waveform, a zero point 0.9 and 10 millivolt peak signal, and this is my output waveform. And we can see this is an amplified output waveform, which is expected because this is a single stage common source amplifier, and also this is an inverting amplifier. So the phase is out of like 180-degree out of phase. So we can see the output is 180-degree out of phase of my input. So this is like a simple analysis if I want to do. Yeah. So this is what we have done using this common source amplifier. Similarly, we can also run AC analysis. So I think now the time is also over. So rather than doing it again, I will try to show you what I have done earlier, and we can quickly see into that. So this is something which I had already built. So the previous schematic was for transient analysis. This was for AC analysis. So the only difference here is this one, the input signal which I have applied. Apart from DC source, it also includes sinusoidal and also AC also. So this statement is required for AC analysis, AC1. I can remove this sinusoidal, it's not required, but let's be there because if AC analysis is not run, this will be of no use sinusoidal here. But this is required for AC analysis and this amplifier remains same. Another important element which I forgot in my previous, but is this adding this ammeter. This is an ammeter component. If I add it here, I can also annotate my DC current through my circuit on this element itself. Okay. And as far as my statement is concerned, for AC analysis, I have made this, I've added this statement here, AC decadal 20 from 1 kilohertz to 5 gigahertz in the steps of 20. In logarithmic steps, it will do. And again, output will be saved here. So this is the statement for AC analysis. I think pretty much everything remains same. So I will quickly show you again how my AC analysis will look like. Again, I run a simulation. And mind you, for AC, I have created another schematic. Although you can do it in the same schematic also, but it's always advisable to build different test benches for different kind of analysis, like for transient or AC. And as part of this bootcamp, I think primarily you will be requiring only these three analyses. One is operating point, DC operating point analysis, transient analysis, and AC analysis. Apart from that, Ngspice has a lot of other capabilities, but I think that you don't require for now. But if you are interested, you can definitely go to the resources and you can check there. Yeah, so simulation has run. So again, first I will check with operating point. Yeah, so these are same. And here you can see, I can also see the DC current, 905 microamperes, which is flowing through my circuit. And now I want to see AC plots, like how my gain varies with my frequency. So for that, plot this, and these plots are generated here. So this is the absolute gain, like 5.8, the absolute gain of 6, or if I want to plot it in dB, it is around 15.38 dB. So that's how the gain got plotted here. Yeah. So yeah, I think this is pretty much for the first lecture. I think we have seen how to use Xschem for building a schematic, then symbol, then test bench, and then how to run simulation on those test bench using Ngspice as a simulator. Okay, so yes, that's all for today. Maybe if anybody has any query, we can quickly discuss.
Any queries, anyone? Pavan. So final netlist, the file generated is going to be used for the next flow layout.
Yes. So whatever, so this is like, let us say whatever results I have got today, the transient is, I am okay, I am happy with that. Like this is the performance. If it is done, then my schematic is freezed and then my netlist is frozen. This netlist I will be using, showing you tomorrow how to build a layout in Magic using this netlist for the same circuit.
So do we have to optimize our layout or netlist for like maximum gain or some particular parameter?
Yeah, in fact that's the role of an analog designer or challenge of analog designer. So right now we are talking about very small circuits, but if you go into an industry, let us say if you are working for a, let us say 6G mobile, this standard has to come in 2020. So the teams working on that, they will be working on a very high frequency, like they want a very high gain at this frequency or a very low power dissipation. So those specifications are given to you as a designer, and your task is to achieve those specifications based on the architecture you have selected and how you basically size your devices and basically decide your component values.
So I was planning to use the GMID plots for optimizing one particular parameter, for example, gain or slew rate or bandwidth, so that
Okay.
I can like check the parasitic effects after tape out.
Yeah, I want to ask, like, you are talking about some other project, or you're targeting for this particular boot camp, like tape out for this boot camp?
For this bootcamp itself, sir, I have like used GM over ID sizing in the past for some of my projects. So I want to use that design methodology in this bootcamp.
Yeah, definitely you can try to do that. But if you're confident and if you have some prior experience of using these tools and analog design flow, you definitely do that. But my suggestion or advice to anybody would be, because there is a limited time period, and these analog steps, when you start doing it, you sometimes take a lot of time, like building a layout, DRC, LVS. So rather than trying to achieve the perfection in your circuit, try to make it workable. Like even if it is not 60 dB or 70 dB, even if it is 55 dB, I think it's okay. Just try to follow the timeline and deadline so that you are able to do it. If you're confident, please go with whatever approach you want to follow. But just take care of timelines, because we have to do this completion by 30th April, because this is a unique opportunity to get your designs fabricated, even if it is not perfect of not achieving a great specification. But at least if you are able to do a workable design and achieve some typical specification, then I think that would be a good achievement. So just take care of timelines.
Okay, sir, I will keep that in mind. Like this is time-bound project and I have to like submit a
Yeah,
design by that.
yeah, sure. And also, as I mentioned, please use not more than four analog pins. You can exclude VDD and VSS, but please not more than four, maybe two, three, even one. One, I think not much is possible, but even if two, three pins or maximum four, not more than that.
One is
Okay,
asking,
so
but if the specs do
so
not meet up to the layout.
So Pawan, if after layout your specs are not meeting, obviously it means the parasitics in your layout are like large. So during layout, so in commercial tools, because these open source tools are still not so advanced, so you have to basically manually see into your layout and judge by the kind of results you are getting and target the nets which might not have been laid out properly. Like you have used very wide net or some interference might be happening between two nets. But in commercial tools, like if you're using Caliber or PVS or Virtuoso kind of tools, so those tools have a very high end capability of catching the parasitics, which might be affecting performance of your circuit. So there you target those nets, which could be the cause of your specs not meeting, a particular spec not meeting. You try to change your layout, improve that net, maybe use multiple metal lines to reduce the resistance, or use a thinner metal to reduce the parasitic capacity, or make them a little farther away from each other if some coupling is happening. So those kind of techniques you use, and then again run the parasitic extraction and then run the simulation again and see if it is like improving. So this kind of becomes an iterative process. Yeah, this is how you do in industry.
Anyone else has any queries?
Yeah, please try these steps, and if any queries, please put it on Slack. I will try to respond you there and help you as much as possible. Okay, then thank you everyone. I think Sumata, we can conclude it for today.
Yeah, we can conclude it.